This is how much I love it. I am going to help you do it. Alright, so we need to talk about this and how recursion allows us to handle it. And it's actually in our textbook. It starts on page 86 of the pair. So this is frequently one of the problems that they give you on the foundation exam for proving that you know how to do it. So what is it in the first place? So what is it's a math house, or a puzzle, and it has they have two different rods and then some number of discs, and they're varying in size. So the smallest one's on the bottom, and the smallest one's on the top, and the big one's on the bottom. So what happens is the puzzle is stuck in a stack on one side, and then the smallest one on the top. So this is kind of what it looks like. So you see in this example here, there's math is hard. 4, 5, 6, 7. There's 8 of them on this one, okay? So depending upon how many discs are on the stack is how many times it takes to actually solve the puzzle. But of course, we're in computer science, so we have us to show us how to do that. So first let me show you the visual reference. It runs in real time, so you can see if you're not familiar with this game. That's an order. So that's how you have to play the game. So you have to get them all moving from the original test to another test. And so the third test is called the helper test, the one that helps you do this. You're missing video. So obviously the more discs there are, the longer it's going to take, the more turns it's going to take for it to actually execute, right? So, modification. Okay, so the objective is the puzzle that's going to use the entire stack. So only one distinct movement at a time. And they have to also make this step on top has to be smaller than the disc on top. And then no disc can be placed on top of the smaller one. So from a calculation perspective, from an equation perspective, with 3 discs, the puzzle itself is 7 units. So that calculation is actually 2 times 2 raised to the power of n. So whatever that value is. So in this case it's 3, so 2 to the raised to the power of n. 2 raised to 30 is 8, and subtract 1 when you get your 7. So that's the minimum number of moves to solve the Taoist norm. So this is something that you will see on your foundation window. It's something very similar to it. So it's very good that you get familiar with this. So so here the first, when we look at this, so the source code is uploaded to my coursing already. So here I just have my function sorted at the top here, and then I have an integer and 3 characters I'm taking as defining as my parameters, and I have my name. And in my name I have about a variable called name.num, and what that does is telling the program you're telling them how many bits there are. Okay, so I didn't know this, and then we're going to do DNS, and we're going to save that into the address of our number. And then here we're going to say what our pegs are. So the pegs are going to be the sequence of moves involved in the application. So here's our initial function call to towers. And then if you come down here, you'll see that we are using recursion to get us through. So what happens is here, all right, so if the number is 1, there's 1 disk, there's 1 move done, right? So, we don't have to do recursion for that one because we're done. But here, okay, otherwise, if we have more than 1, then you're going to see that we're going to start moving the disk back and forth to accommodate that. So when we run this, right, so to match our visuals, we're going to put insert. All right, so if we watch this, so the first one is move this 1 from peg A to peg B. So let's look at this. So the first move, this is peg A to peg B, obviously you can see, okay? So here, the next first move is move A to B, all right? So we've taken that smallest disk on top and we've moved it over here to B. And so that, from a program perspective, you can see is the first move that it came up with A to B. And then after that, so because of the rules, we cannot put disk 2 on top of disk 1 because it's bigger, right? You're not allowed to do that. It only has to be 1 on the bottom. So our only option is at this point to move from peg A to peg C. And so you'll see that the code actually does that. So let's look at the code. Like, okay, so the first time through, our number -1. So we came in here with so first time through, towers are called the disks. And so our from peg is A, our to peg is B, and our auxiliary peg is C. And so it's telling us which peg is the correct one to actually move it. So here, when we get to this logic, we come in and we have a 3. 3 minus 1 is 2. And then we're going to say our from peg, our aux peg, and our to peg. We're changing the order. So that's going to allow us to do this first move here. We're moving okay? The second time through, that means it's not going to be so the second time through, we see here where it is going to call with 2 disks. on A and going to move 1 from A to C. Okay, because it keeps moving through the second column. So here we have our second call. So we moved our first one for 3. Then we come down here, and now we're going to move our next one. And do the recursion as we call previous. You see, we keep calling ourselves. So every time we come through. So we came through here first time with 3, right? And then we are calling ourselves again. So now when we minus 1, so then we have 2, and then minus 1, so now we have 1. And so when you look at the output here, you can see how it's moving with this. And so power call through this, A to B and C. And then power call to this, and power call with 1 bit. So again, we're back to that stacking that we talked about on Monday, where it's stacking the function calls on top of each other. So just like we did when we were doing the calculation on the math there, we're doing our sum of squares. We're now doing the same thing, except we're doing it with these function calls to the power so that we can add them in. So you see, if you look at this, look at the outputs. The first thing I'm doing is you see I have 3 instances of this that is being outputted right away. And then you start seeing where the individual function calls are happening one after another as it moves through the number until we get down to 1. And again, if you look here, remember, if num equals 1, then we actually move that this. See that? No. Come on, it's right here. How can you not do that? This? No. Okay. So you see the output here. So it comes in here, we have that one function call, and then we come in and say, okay, so is num equal to 1? And it's not. It's actually equal to 3 the first time it comes in here. So now it calls itself with the 2, and then it calls itself again with the 1. So that's why you're seeing these 3 function calls stacked on top of each other. Does that make sense? If you look at it sequentially, it's exactly what it's doing. So then we start doing the different moves. Here we did. So you look at the slide, the first one we're moving is this A to this 1, this moves 2. So it should be 1 and 2 here, right? That matches the operation. So I move my this 1 from peg A to peg B. And then the next thing you see here is we're going to move this 2 from A to C. So come down here, move this 2 from A to C. And then the next thing you see here is that we're calling ourselves again. Oh, I have 1 bit left, so I need to move that guy from C to A. This is killing me. Last time I was putting it together, I'm like, oh, I'm so lost. So when we move that next bit, so we have to be able to get those types of resiliencies. This ends up with the guys in the middle. All right, so I think the code ends up with the guys over at C. But I had changed that code to end up at C. C was our auxiliary head. Yeah. Alright, so move this 1. We got this first distance over here, right? And now we have to move the next one. And so now we move, the only other peg available and following the rules is moving A to C. So then we have to make another move in order to move the stack. And so our only option is, because we don't want to go back this way, because we want it to be one of these 2 pegs. So our option is to move A over to C. So then we get to the point where we can put the smaller one that's on B on top of C, move the largest one on the bottom for B. So now we've started our stack where we're going to move the power. So the next step, the most logical step, is to move the smallest one over here to get it out of the way so that we can put that second largest one in the middle. So that move looks like this. And then finally we move that second largest one on top of that peg. And then finally we put the smallest one. So again, from a visual perspective, without my little pictures. You can see how it runs through that process. And this one is with 4 hits, so it's going to take a little more time, but you can see how. Now, which head do you have to move it to? Usually, like from a foundation exam perspective, they'll probably either head C or head D. That's the stack that they end up on. And it doesn't change the process, it just changes the way that you move the actual hit. So from a code perspective, let's look at this again. You can see what we're doing. You kind of see this guy running over here. So here, we have the sequence of moves involved in the power of Hanoi. The powers are called with 3 bits, then 2, then 1. Because it's 1, 2, going through. So in this case, let's do 4 so that we can match the visual on the monitor. See if our implementation matches theirs. Okay, so if we have 4 disks, you see it recursively calls itself for all 4 of those disks, and now it's stacking these function calls on top of each other. So then when it starts doing its different moves, okay, so move this A to C. See, this one did A to B. So it depends upon what the whole thing which one it is. So I could probably, if we flip it, and how we do that, how we change which order it goes into is right here. So we change. Should be able to get that there. Match the output. So here we have our 4 disks. So now we're moving A to B. So now it's matching the output. Then we move A to C, and then we're moving B to C. Is it following it? No, it's just how it is now. How do you implement that? So the thing about the power of Hanoi, what it is, it's just an implementation of recursion that allows you to solve a complex problem. And so what we end up doing here is every time we go through and call the recursion itself, that when we get to the point where our num equals 1, that's when it starts moving like this. And so it stacks those function calls on top of each other. So like we have our stack here. So this is going to be that first time it calls it at the bottom here. It's the first time it's going to call it with that value of 4. And then the next time it's going to call it with the value of 3, and then 2, and then 1. And then it's going to stack all the function calls on top of each other until it gets to all of them that we need. And so what you can do is to see how many times it's actually calling. Is that you'll create yourself a counter. So one of the questions that you get asked is, first of all, what is the minimum number of bits for that solution? Okay, and so this is the equation here. The minimum number of bits is based on this equation here. So whatever value the user inputs for the number of bits is equal to 2 to that power and 0 minus 1. So in the case of the 4 disks, so 2 raised to 4 is. Yeah, thank you. Minus 1. So the number of moves is actually 15. And so what that does for you is it allows you to know what the solution is, and then you can go through and actually come up with the solution itself. And so sometimes I think I have to I have to talk to Ruth and find out what it is. Sometimes these codes you actually have to whiteboard it, sometimes you have to pseudocode it. So it would just depend on what the request is. But this is one of the things that you definitely need to understand from a recursion perspective because it's very high odds of this being on your foundation exam. And so the code here again, if you just want to walk through it. So we call this guy. So here, we get a number of this, and then we call the function of this time. And now we're going to use recursion. So this is telling you what the end tag is. Is it going to be the center one? Is it going to be an end? Is it going to be the last one? And so that's one of the things you need to know. The tag is the goal. Because that's the one that you need to make sure that you start getting the biggest one on the bottom. And so here, you can see that when I have my function call, the first time you'll see I come in here and have my print statement. And then I check to see if it's 1. And if it is 1, I'm going to specifically move this one from my type 2 to 2. Okay? So I just explicitly am moving that 1 bit. Otherwise, I need to come down here and start using my auxiliary types in order to do the move. And so here again, at this point, you can see the output. So if this is free, see my first 3 function calls in here to get my free, get them on the stack. And then as we reduce the value of num, we get to the point where we are moving our bits. Does make any sense? Yeah. And wherever you're going, just stop that. Is there any questions about this? This is something, is there a way I could better explain this? Yes.
So we'll only have to worry about how many disks, not how many, so the pegs will always be the same, but the number of disks.
The pegs are always the same, yeah. The only thing that changes is the number of disks. It's usually a minimum of 3. So if you guys don't have any questions, I wanted to go through this. This is something that you definitely see on the foundation exam. I want you to understand it. I need you to go through it and walk through it and make sure you do understand it. And if you have questions, I need you to ask them. It will definitely be on your next exam because it really is that important. Recursion really is that important. And we'll have a actual homework assignment based on recruiting as well. And you're not going to wait until the business really started, right? You shake your head, yeah, you're happy. Okay, thank you. All right. So take a look at the code, go look at the video, watch it, understand it. Definitely something you need for your foundation exams. Really, really important to understand recruiting. So we'll have, there's an additional lecture on Friday for recruiting to finish out chapter 3, and then I will have the next one with the subject put together for Friday to make it over that. So unless you have any questions, today is a nice short day. So if I have people that still have code issues, we have 20 minutes, and so I will